A monsoon of the Indian subcontinent is among several geographically distributed observations of global monsoon taking place in the Indian subcontinent. In the subcontinent, it is one of oldest weather observations, an economically important weather pattern over June through September every year, and the most anticipated weather event and unique weather phenomenon. Yet it is only partially understood and notoriously difficult to predict. Several theories have been proposed explaining the origin, the process, the strength, the variability, the distribution and the general vagaries of the monsoon of the Indian subcontinent, but understanding of the phenomenon and its predictability are still evolving. The unique geographical features of the subcontinent, along with associated atmospheric, oceanic and geophysical components, are influential in ensuring the anticipated behavior for a monsoon in the Indian subcontinent. Due to its effect on agriculture, flora and fauna and the general weather of India, Bangladesh, Bhutan, Pakistan, Sri Lanka, etc., among other economic, social and environmental effects, a monsoon is one of the most anticipated, followed and studied weather phenomena of the Indian subcontinent. It has significant impact on the overall well-being of subcontinent residents and has even been dubbed the real finance minister of India. Definition: Monsoon, derived from the Arabic word mawsam meaning season, although generally defined as a system of winds characterized by a seasonal reversal of its direction, lacks a consistent detailed definition. Some examples are given below. The American Meteorological Society defines it as a name for seasonal winds, first applied to the wind blowing over the Arabian Sea from northeast for 6 months and southwest for 6 months. Later it has been extended to similar winds in other parts of the world. Intergovernmental Panel on Climate Change describes monsoon as a tropical and subtropical seasonal reversal in both the surface winds and associated precipitation, caused by differential heating between a continental scale landmass and the adjacent ocean. Indian Meteorological Department defines it as the seasonal reversals of the wind direction along the shores of the Indian Ocean, especially in the Arabian Sea, that blow from the southwest during one half of the year and from the northeast during the other half. Colin Stokes Ramage in Monsoon Meteorology, International Geophysics Series, Volume 15, defines monsoon as a seasonal reversing wind accompanied by corresponding changes in precipitation. Monsoon of the subcontinent is primarily noted for its rain-bearing ability and for the associated unpredictability of the weather. Consequently, some definitions incorporate rain in its definition. Background: observed initially by sailors in the Arabian Sea traveling between Africa, India and Southeast Asia, monsoon is a major weather phenomenon in India for the influence it casts on the lives of its inhabitants for centuries. Monsoon in India can be categorized into two branches based on their spatial spread over the subcontinent, Arabian Sea branch, Bay of Bengal branch. Alternatively, it can be categorized into two segments based on the direction of rain-bearing winds, southwest monsoon, northeast monsoon. Based on the time of the year that these winds bring rain to India, they can also be categorized in two rain periods called the summer monsoon, the winter monsoon. The complexity of monsoon as a weather phenomenon of India is not yet completely understood, making it difficult to accurately predict its behavior in terms of quantity, temporal and spatial distribution of the accompanying precipitation. These are the most monitored components of monsoon determining the water availability in India for any given year. Mechanism of monsoon. Monsoon is a tropical phenomenon. The Indian subcontinent lies northwards of the equator up to the Himalayas and Hindu Kush, primarily in the tropical zone of the northern hemisphere. The weather pattern involves winds blowing from the southwest direction from the Indian Ocean onto the Indian landmass during the months of June through September. These are generally rain-bearing winds, blowing from sea to land, and bring rains to most parts of the subcontinent. They split into two branches, the Arabian Sea branch and the Bay of Bengal branch near the southernmost end of the Indian peninsula. They are eagerly awaited in most parts of India for their agricultural and economic importance. Subsequently later in the year, around October, these winds reverse direction and start blowing from a northeasterly direction. Given their land-to-sea flow, from subcontinent on to the Indian Ocean, this system carries less moisture and brings rain to only limited parts of India like Kerala, Andhra Pradesh and Tamil Nadu. This is known as the northeast monsoon. However, this rain is responsible for the rice bowls of South India. This mechanism completes the annual monsoon cycle of the Indian subcontinent. Effective geographical relief features: although the SW and NE monsoon winds are seasonally reversible, they do not cause precipitation on their own. Two factors for rains are essential for rain formation: moisture-laden winds, droplet formation. Additionally, one of the causes of rain need to happen, which in this case is primarily orographic due to presence of highlands right across the paths of the winds. Orographic barriers in the path of a wind force it to rise. Consequently, precipitation occurs on the windward side of highlands due to adiabatic cooling and condensation of the rising motion of the moist air. For all the above scenarios to fulfill simultaneously, the unique geographic relief features of Indian subcontinent come into play. The notable features of Indian subcontinent, required in explanation of the monsoon mechanism, are as follows. First is the presence of abundant water bodies around the subcontinent: Arabian Sea, Bay of Bengal and Indian Ocean. These help in accumulation of moisture in the winds during the hot season. Second is the presence of abundant highlands like the Western Ghats and the Himalayas right across the path of the SW monsoon winds. These are the main cause of the substantial orographic precipitation all over the Indian subcontinent. The Western Ghats are the first highlands of India that the SW monsoon winds encounter. The Western Ghats rise very abruptly from the western coastal plains of the subcontinent, making effective orographic barriers for the monsoon winds. The Himalayas play more than the role of just the orographic barriers for monsoon. They help in its confinement onto the subcontinent. Without it, the SW monsoon winds would blow right over the Indian subcontinent into Tibet, Afghanistan and Russia without causing any rain. For any monsoon, the highlands of eastern Ghats play the role of orographic barrier. Features of monsoon rains: there are some unique features about the rains that monsoon brings to the Indian subcontinent. Bursting of monsoon rains. Bursting of monsoon implies the onset of the sudden change in weather conditions in India due to abrupt rise in the mean daily rainfall. Similarly, the burst of any monsoon marks an abrupt increase in the mean daily rainfall over the affected regions. Monsoon rain variability: one of the most commonly used phrases to describe the erratic nature of the monsoon of the Indian subcontinent is vagaries of monsoon, used in newspapers, magazines, books, web portals to insurance plans and India's budget discussions. In some years, it rains too much causing floods in several parts of India, in others it rains too little or not at all causing droughts. In some years when the rain quantity is sufficient, its timing may be arbitrary. In some years, in spite of average annual rainfall, its daily distribution or the areal distribution might be substantially skewed. Such is the variability in the nature of monsoon rains and weather. Ideal and normal monsoon rains. Every year the normal onset of SW monsoon is expected to burst onto the western coast of India around June 1, covering entire India by around July 15. Its withdrawal from India typically starts from September 1 onwards and completes by around October 1. Similarly, the NE monsoon is expected to burst around October 20 and last for a period of about 50 days before withdrawing. However, a rainy monsoon is not necessarily a normal monsoon. A normal monsoon is expected to perform close to its statistical averages calculated over a significantly long periods. Therefore, a normal monsoon is generally accepted to be the monsoon that has near average quantity of precipitation over all the geographical locations under its influence and over the entire expected time period of its influence. Additionally, the arrival date and the departure date of both the SW and NE monsoon should be close to the mean dates. The exact criteria for normal monsoon is defined by the Indian Meteorological Department with calculations for the mean and standard deviation for each of the aforesaid precipitation variables. A monsoon with excess rain can cause floods in, and one with too little rain can lead to widespread drought, food shortage, famine and economic losses. Therefore, a normal monsoon with mean performance is the most desirable monsoon. Theories for mechanism of monsoon. Theories for mechanism of monsoon primarily try to explain the reasons for the seasonal reversal of winds and the timings of their reversal. Traditional theory. Due to difference in the specific heat capacity of land and water, continents heat up faster than the seas. Consequently, the air above the coastal land heats up faster than air above seas. This creates areas of low air pressure above coastal lands compared to the air pressure over the seas, causing winds to flow from the seas onto the neighboring lands. This is known as sea breeze, process of monsoon creation. Also known as the thermal theory or the differential heating of sea and land theory, it portrays the monsoon as a large-scale sea breeze. It states that during the hot subtropical summers, the massive landmass of Indian Peninsula heats up at a different rate than the surrounding seas, resulting in a pressure gradient from south to north. This causes flow of moisture-laden winds from sea to land. On reaching the land, these winds rise up due to the geographical relief, cooling adiabatically and leading to orographic rains. This is the southwest monsoon. Reverse happens during winter when the land mass is colder than the sea, establishing a pressure gradient from land to sea. This causes the winds to blow over Indian land mass towards Indian Ocean in a northeasterly direction, causing the northeast monsoon. Since the SW monsoon is from sea to land, it has more moisture than the NE monsoon. Only a part of the NE monsoon passing over Bay of Bengal picks up moisture, causing rain in Andhra Pradesh and Tamil Nadu during the winter months. However, many meteorologists argue that the monsoon is not a local phenomenon as explained by the traditional theory, but a general weather phenomenon along the entire tropical zone of Earth. This criticism does not deny the role of differential heating of sea and land in generating monsoon winds, but merely restricts it to one of the several factors rather than the only one. Dynamic theory. The prevailing winds of the atmospheric circulation arise due to the difference in pressure at various latitudes of Earth and act as means for distribution of thermal energy on the planet. This pressure difference is due to the differences in solar insolation received at different latitudes of Earth and the resulting uneven heating of the planet. Alternating belts of high pressure and low pressure develop along the equator, the two tropics, the Arctic and Antarctic circles, and the two polar regions, giving rise to the trade winds, westerlies and the polar easterlies. However, the geophysical factors like revolution of Earth, its rotation and axial tilt of the Earth result in gradual shifting of these belts northwards and southwards following the sun's seasonal shifts. Process of monsoon creation. The dynamic theory of monsoon explains monsoon on the basis of the annual shifts in the position of global belts of pressure and winds. According to it, monsoon is the result of the shift of the intertropical convergence zone under the influence of the vertical sun. Though the mean position of the ITCZ is taken as the equator, it keeps shifting northwards and southwards with the migration of the vertical sun towards the tropics during the summer of the respective hemispheres. As such, the theory states that during the northern summer, the ITCZ moves northwards, along with the vertical sun, towards the Tropic of Cancer. The ITCZ, being the zone of lowest pressure in the tropical region, is the target destination for the trade winds of both the hemispheres. Consequentially, with ITCZ at the Tropic of Cancer, the southeast trade winds of the southern hemisphere have to cross the equator to reach the ITCZ. However, due to Coriolis effect, these southeast trade winds are deflected eastwards in the northern hemisphere, transforming into southwest trades. These pick up the moisture while traveling from sea to land and cause orographic rain once they hit the highlands of the Indian Peninsula. This results in the southwest monsoon. The dynamic theory provides the explanation of the system of monsoon as a circumglobal weather phenomenon rather than just a local one. And when coupled with the traditional theory, it enhances the explanation of the differential intensity of precipitation impact of monsoon along the coastal regions with orographic barriers. Jet stream theory. This theory tries to explain the establishment of both the NE and SW monsoons as well as unique features like bursting and variability. The jet streams are a system of upper air westerlies. It gives rise to slowly moving upper air waves, with 250 knots winds in some airstreams. First observed by World War II pilots, they developed just below the tropopause over areas of steep pressure gradient on the surface. The main types are the polar jets, the subtropical westerly jets and the less common tropical easterly jets. They follow the principle of geostrophic winds. Process of monsoon creation. Over India, a subtropical westerly jet develops in the winter season which is replaced by the tropical easterly jet in the summer season. The high temperature over the Tibetan Plateau, as well as over Central Asia in general, during the summer is believed to be the critical factor leading to the formation of the tropical easterly jet over India in summer. The mechanism affecting monsoon is that the westerly jet causes high pressure over northern parts of the subcontinent during the winter. This results in the north-to-south flow of the winds in the form of the NE monsoon. With the northwards shift of the vertical sun, this jet shifts northwards too. The intense heat over the Tibetan Plateau, coupled with associated terrain features of high altitude of the plateau, etc. generate the tropical easterly jet over central India. This jet creates a low-pressure zone over the northern Indian plains influencing the wind flow towards these plains, assisting the establishment of the SW monsoon. Theory for bursting of monsoon. The unique feature of bursting of the monsoon is primarily explained by the jet stream theory and the dynamic theory. Dynamic theory. According to this theory, during the summer months of Northern Hemisphere, the ITCZ shifts northwards pulling the SW monsoon winds onto the land from the sea. However, the huge land mass of the Himalayas continue to restrict the low-pressure zone onto the Himalayas itself. It is only when the Tibetan Plateau heats up a lot more than the Himalayas does the ITCZ abruptly and swiftly shift northwards, leading to burst of monsoon showers over the Indian subcontinent. The reverse shift takes place for the NE monsoon winds, leading to a second minor burst during the Northern Hemisphere winter months of NE monsoon rainfall over eastern Indian peninsula. Jet stream theory. According to the theory, the onset of SW monsoon over Indian subcontinent is driven by the shift of the subtropical westerly jet northwards from over the plains of India towards the Tibetan Plateau. This shift is due to the intense heating of the plateau during the summer months. This shift of the westerly jet to the north of the Himalayas is not a slow and gradual process, as expected for most changes in weather pattern. The primary cause of these is believed to be the height of the Himalayas. As the Tibetan Plateau heats up, the low pressure created over it pulls the westerly jet northwards. Due to lofty Himalayas, the westerly jet is inhibited from moving northwards. However, with continuous dropping pressure, sufficient force is created for the movement of the westerly jet across the Himalayas after a significant period. As such, the shift of the jet is sudden and abrupt, causing the bursting of SW monsoon rains onto the Indian plains. The reverse shift happens for the NE monsoon. Theories for monsoon variability. The jet stream effect. The above-mentioned jet stream theory also explains the variability in timing and strength of the monsoon timing. A timely northward shift of the subtropical westerly jet in the beginning of the summer season is critical to the onset of the SW monsoon over India. If the northward shift of this jet is delayed, so is the SW monsoon. An early shift heralds in an early monsoon strength. Additionally, the strength of the SW monsoon is determined by the strength of the easterly tropical jet over central India. A strong easterly tropical jet results in a strong SW monsoon over central India and vice versa. El Niño plus or minus O Southern Oscillation Effect. El Niño plus or minus O is a warm ocean current originating along the coast of Peru that replaces the usual cold Peru or Humboldt current. This warm surface water reaching towards the coast of Peru with El Niño plus or minus O is pushed westwards by the trade winds, thereby raising the temperature of the southern Pacific Ocean. A reverse condition is known as La Niña plus or minus A. Southern Oscillation, a phenomenon first observed by Sir Gilbert Thomas Walker, Director General of Observatories in India, refers to the seesaw relationship of atmospheric pressures between Tahiti and Darwin, Australia. He noticed that when it was high pressure in Tahiti, it was low pressure in Darwin and vice versa. A Southern Oscillation Index, based on the pressure difference between Tahiti and Darwin, has been formulated by the Bureau of Meteorology to measure the strength of the oscillation. Walker noticed that the quantity of rainfall in the Indian subcontinent was often negligible in the years of high pressure at Darwin. Conversely, low pressure at Darwin bode well for the precipitation quantity in India. Thus he established the relationship of southern oscillation with quantities of monsoon rains in India. Ultimately, it was realized that the southern oscillation is just the corresponding atmospheric component of the El Niño plus or minus O La Niña plus or minus O effect. Therefore, in the context of the monsoon, the two cumulatively came to be known as the ENSO. The ENSO is known to have a pronounced effect on the strength of SW monsoon over India, with the monsoon being weak during the El Niño plus or minus O years, whereas La Niña plus or minus A years have particularly good monsoon strength over India. Indian Ocean Dipole effect. Although ENSO was statistically effective in explaining several past droughts in India, in the recent decades the ENSO-monsoon relationship seemed to weaken in the Indian subcontinent. For example, the 1997, strong ENSO failed to cause drought in India. However, it was later discovered that just like ENSO was an event in the Pacific Ocean, a similar seesaw ocean atmosphere system in the Indian Ocean was also at play. It was discovered in 1999 and named the Indian Ocean Dipole. An index to calculate it was also formulated. IOD develops in the equatorial region of Indian Ocean from April to May, peaking in October. With a positive IOD, winds over the Indian Ocean blow from east to west. This results in the Arabian Sea being much warmer and eastern Indian Ocean around Indonesia becoming colder and dry. In the negative dipole year, reverse happens, making Indonesia much warmer and rainier. It was demonstrated that a positive IOD index often negated the effect of ENSO, resulting in increased monsoon rains in several ENSO years like the 1983, 1994 and 1997. Further, it was shown that the two poles of the IOD, the eastern pole and the western pole, were independently and cumulatively affecting the quantity of rains for the monsoon in the Indian subcontinent. Equatorial Indian Ocean oscillation. Similar to ENSO, the atmospheric component of the IOD was later discovered and named as Equatorial Indian Ocean Oscillation. When ENSO effects were factored into the statistics, certain failed forecasts, like the acute drought of year 2002, could be further accounted for. The relationship between extremes of the Indian summer monsoon rainfall, along with ENSO and ENSO, have been studied, and models for enhanced predictability of the quantity of monsoon rains have been statistically derived. Monsoon rain prediction models. Since the Great Famine of 1876–78 in India, various attempts have been made to predict the rainfall during the monsoons in India. At least 5 models for prediction of monsoon rains exist in India. Seasonal Prediction of Indian Monsoon Center for Development of Advanced Computing at Bengaluru is facilitating the seasonal prediction of Indian monsoon experiment on the PARAM Padma supercomputing system. This project did simulated runs on historical data from 1985 to 2004 to try and establish the relationship between the 5 atmospheric general circulation models with the monsoon rainfall distribution. Indian Meteorological Department Model IMD has tried to forecast the monsoon for India since 1884, some unsuccessfully, but till 2011 is the only official agency entrusted with making public forecasts about the quantity, distribution and timings of the monsoon in India. IMD's position as the sole authority on the matter was further reiterated in 2005 by the Department of Science and Technology, New Delhi. In 2003, IMD underwent a substantial change in its forecast methodology, model as well as its administration. A 16-parameter monsoon forecasting model used by the Indian Met Office since 1988 was revamped in 2003 with a new one. However, following the 2009 drought in India, IMD decided in 2010 that it needed to develop an indigenous model to further enhance its prediction capabilities. Significance. Indian monsoon is the primary delivery mechanism for fresh water in the Indian subcontinent. As such, it impacts the environment, agriculture, society, hydropower production and geography of the subcontinent, with all these factors cumulatively contributing towards the health of the economy of affected countries. The Indian monsoon turns large parts of India from a kind of semi-desert into green grasslands. See photos only taken 3 months apart in the Western Ghats. Geographical, Mosinram and Shirapunji. both in the Indian state of Meghalaya alternate to be the wettest places on Earth given the quantity of their rainfall. There are other cities with similar claims but with 200,000 of rain for each of these locations. Monsoon of Indian subcontinent is a significant contributor towards the water supply of its area of influence. Agricultural, India, historically an agrarian economy primarily, has recently seen the services sector overtaking the farm sector in terms of GDP contribution. However, even today agriculture sector contributes 17 to 20% of GDP and is the largest employer in the country with about 60% of people dependent on it for employment and livelihood. The land use pattern of India indicates that 49% of land is under agriculture in India. It is 55% if associated wetlands agriculture, drill and farming areas, etc. are included. Since over half of these farmlands are rain-fed, monsoon is critical to the food sufficiency and quality of life for the country. Despite progress in alternative forms of irrigation, agricultural dependency on monsoon is far from insignificant, even today. Therefore, the agricultural calendar of India is governed by monsoon. Any fluctuations in the time distribution, spatial distribution or quantity of the monsoon rains may lead to conditions of floods or droughts causing the agricultural sector to adversely suffer. This has a cascading effect on the secondary economic sectors, the overall economy, food inflation and therefore the overall quality and cost of living for the general population in India. Economic. The economic significance of monsoon can be aptly summed up by Pranab Mukherjee's statement that monsoon is the real finance minister of India. A good monsoon resulting in improved agricultural brings down prices of essential food commodities and reduces their imports overall reducing the food inflation. Further improved rains result in increased hydroelectric production. All these factors initiate positive ripple effects throughout the economy of India. Social D. Subbaray, during a quarterly review of the monetary policy, once highlighted that lives of Indians depends on the performance of monsoon. His own personal career prospects, emotional well-being and the performance of his monetary policy were all a hostage to monsoon like it was for most Indians. Additionally, farmers, rendered jobless due to failed monsoon rains tend to migrate city wards. This crowds the city slums and further aggravates the job, infrastructure and sustainability of city life. Such is the magnitude of effect that monsoon casts on the lives of Indians. Travel. In past, people usually refrained from traveling during monsoons for practical as well as religious reasons. But with advent of globalization, travel during monsoons is gaining popularity. Places like Kerala, Western Ghats get a very large number of tourists, both local and foreigner during monsoon season. Kerala is one of the top destinations for tourists interested in Ayurvedic treatments and massage therapy. One major drawback of traveling during monsoons is the fact that most of wildlife sanctuaries are closed during this rainy season. Also, some mountainous areas, especially in Himalayan regions, get cut off due to damaged roads caused by landslides and floods during heavy rains. Environmental. The monsoon is the primary bearer of fresh water to bodies of water in the area. The peninsular Deccan rivers of India are mostly rain-fed and non-perennial in nature depending primarily on the monsoon for water supply. Similarly, most of the coastal rivers of western India are rain-fed and monsoon-dependent. As such, obviously the flora, fauna and the entire ecosystem of these areas are heavily dependent on the monsoon. Notes: the name of the wind is based on the direction that it blows from. Therefore, southwest winds imply that the winds are blowing onto the land from the southwest direction. Similarly, northeast wind implies air flowing from northeast towards southwest onto the land. The Aravalli Mountains also lay in the path of the SW monsoon but do not result in much precipitation because they are in the direction of the path of the SW winds and not across them, causing no orographic lift of the winds. Other major highlands like Cardamom Hills, Anamalai Hills and Nilgiri Mountains, playing active roles in the monsoon, are considered major extensions of the Western Ghats and thus not discussed separately. Firstly, Himalayas serve as orographic barriers to the SW monsoon winds. Secondly, they help in the confinement of monsoon within the subcontinent region, hampering their northward progress. Thirdly, they help in the convergence of the Bay of Bengal branch and Arabian Sea branch of the SW monsoon winds, increasing the precipitation intensity over the northern part of the subcontinent. Fourthly, they are a major factor in the bursting of monsoon as per the jet stream theory. Fifth, they assist in the determination of directionality of the Bay of Bengal branch for any monsoon. Their role is still a matter of active study, and our understanding about them is evolving regularly. When the southeast trade winds cross the equator, in the northern hemisphere they are also perceived as equatorial westerlies, since they seem to blowing from the equator towards the Tropic of Cancer. Similarly, due to the ITCZ being at Tropic of Cancer, the northeast trades are confined to the north of the Tropic of Cancer. Change of direction or origin of winds changes their nomenclature as noted above. Geostrophic winds blow parallel to the isobars and keep low pressure zone to their left in the northern hemisphere and to the right in the southern hemisphere. The reversal is a result of the Coriolis effect. See also: monsoon, North American monsoon, monsoon trough, climate of India, Asian brown cloud, tropical monsoon climate, Tibetan plateau, Himalayas, prevailing winds, jet stream, rain, Walker circulation, Indian Peninsula, Indian Meteorological Department, drought in India, Andhra Pradesh, monsoon, references. External links: Indian Meteorological Department official website, Centre for Development of Advanced Computing, Monsoon Online, an Indian Institute of Tropical Meteorology, Pune, India initiative.